Today, the European Organization for Nuclear Research, CERN, is presenting 3 new particles and exposing the subtleties of another particle smasher that may hold the key to understanding the formation of our universe and its destiny. Recent discoveries made by CERN scientists have the potential to fundamentally alter how we understand the universe. Beneath the surface of these gigantic experiments is a broad expanse of particles and forces so strange they could be taken directly out of science fiction, ranging from particles that threaten the fundamental foundations of reality to potential gates to alternate realms. What perplexing secrets are these experiments hiding? Could we explore the realm of CERN and discover information that might cause us to rethink how we perceive the universe? The largest and most potent particle smasher in the world is called the Large Hadron Collider, LHC, and it is situated close to Geneva on the French-Swiss border. Stretching over 27 kilometers and situated deep underground, it holds many mysteries about this remarkable facility that the general public is not yet aware of. Secrets that have the potential to fundamentally alter our understanding of physics and the universe. This enormous scientific tool is run by CERN, the European Association for Nuclear Research, and it enables physicists to test a variety of particle physics theories. This includes well-known analyses of particle physicists' standard model, which aids in our comprehension of the universe's basic components. Fundamentally, protons are accelerated by the LHC to almost the speed of light, and then collide with one another to produce a shower of new particles that scientists investigate to learn more about the rules of nature. In 2012, a pivotal point in particle physics was reached when the Higgs boson, also known as the God particle, was identified through these kinds of tests. This discovery confirmed the process by which particles acquire mass. The experiments carried out at the Large Hadron Collider, LHC, are essential for comprehending circumstances that mimic those immediately following the Big Bang, offering important insights into the origins and evolution of the universe as well as the basic components of matter. Because of this, the LHC holds great promise for discovering previously undiscovered facets of reality, such as dark matter and the basic forces of nature. High-level experimentation at CERN is not without its worries, though. High-energy experiments may produce black holes or other exotic stuff that could endanger life on Earth, according to certain theories. However, CERN makes sure that all safety precautions are taken, and reputable experts keep a close eye on these evaluations. According to theoretical models, there are very few potentially harmful situations. Through its ongoing research and experiments, CERN advances our understanding of the universe and demonstrates the amazing potential of human ingenuity and teamwork in the search for knowledge. The modern marvel of humanity is the LHC. It is a marvel of contemporary science and engineering, not just an amazing piece of technology. The collider is the largest particle collider in the world and one of the main tools in the field of particle physics. It is situated as deep as 175 meters below and spans a tube that is 27 kilometers wide. The LHC's main ring is located in a 3.8-meter diameter tunnel that is joined by 2 parallel beam pipes, allowing it to conduct experiments of extraordinary magnitude. With the help of many superconducting magnets, each pipe rapidly accelerates protons in opposing directions. The proton's route is bent at nearly the speed of light thanks to these magnets, which are essential for guiding them along it. In order to keep the superconducting magnets at their operating temperatures, layers of cooling systems that are kept at temperatures lower than space surround the beam pipes. The utilization of thousands of magnets, comprising 1,232 dipole magnets for beam bending and 392 quadrupole magnets for beam focusing, draws attention to the magnitude of the LHC. The collider's enormous physical scale and creative ambition are demonstrated by the largest and most potent superconducting magnets, which are employed. They are each 35 tons in weight and 15 meters long. The main objective of the LHC is to investigate the smallest constituents of matter in order to gain insight into the fundamentals of the universe. Scientists can analyze the resultant particles formed during these collisions by speeding particles to almost the speed of light and then colliding them with one another at the LHC. As the current best explanation of the subatomic universe, the standard model of particle physics needs to be tested and expanded upon, and this method is essential to do just that. Deciphering the Higgs boson's mysteries is one of the main goals of the LHC's experiments. Its 2012 discovery at CERN supported hypotheses on the mass gain of particles. In addition, the LHC explores other important particles and forces, answering basic inquiries concerning dark matter and the nature of the universe in the early universe following the Big Bang. The goal of the LHC is to verify the existence of new particles that have not yet been observed but are predicted by speculative physics. These studies are crucial to the possibility of finding novel physics outside the standard model, such as supersymmetry and features outside of the traditional three-dimensional viewpoints. The goal of the LHC is to not only determine the structure of the cosmos, but also to promote international cooperation among thousands of researchers from more than 100 countries. The LHC is evidence of global cooperation in the pursuit of knowledge. Its size and design enable it to address the most important physics problems, and its motivation goes beyond simple scientific curiosity. It seeks to transform our understanding of the cosmos and foster international cooperation in science. How does the genuine LHC operate? The LHC, at the center of CERN's research facilities, acts as a potent magnifying glass into the quantum realm, enabling researchers to examine the crucial particles that make up the universe. One important technique for testing the fundamentals of physics is the process of particle acceleration and collision at the LHC. Two beams of high-energy particles enter the collider and travel almost as fast as light before meeting. These beams replicate space conditions as they pass through tubes maintained at extremely high vacuum. At specific impact places throughout the tunnel, superconducting electromagnets that have been cooled to temperatures lower than space assist in focusing and steering the beams. With tremendous energy, these beams hit and smash particles together to create a range of subatomic particles, some of which are incredibly unstable and exist for only a few seconds. The LHC is outfitted with 4 enormous detectors, ATLAS, CMS, ALICE, and LHCb, that are tailored to different kinds of analysis in order to identify and examine the results of these collisions. The mass, charge, and energy of the particles are all recorded by these detectors. Scientists can use this information to study the particles and forces that govern the cosmos and to evaluate predictions made by particle physics models, such as the Standard Model. The discovery of the Higgs boson in 2012 was one of the most important findings at the LHC. This particle, which is sometimes called the God particle, is important because it supports the existence of the Higgs field, which gives fundamental particles their mass. The Standard Model predicted the existence of the Higgs boson, and its discovery verified long-held theoretical predictions, constituting a historic accomplishment. The Higgs boson has not been the only particle discovered thanks to the LHC. For example, it has verified the existence of tetraquarks, which are particles made up of 5 quarks, and evidenced the existence of pentaquarks, which were previously unobserved. These findings add to our knowledge of hadronic matter, which consists of quarks held together by the strong force, the same force that maintains the integrity of atomic nuclei. These discoveries show how well the Standard Model predicts the behavior of matter in extreme circumstances, such as the early stages of the Big Bang. And they also pave the way for new research directions in particle physics. Strangelets and small black holes are examples of speculative threats that have sparked scientific inquiry and public attention. Theorized to be more stable than regular matter, strangelets are hypothetical particles that have the ability to change any matter they come into contact with into odd matter. This notion raises the risk that strangelets created in particle collisions at the LHC could set off a disastrous chain reaction that would turn all matter on Earth into weird matter. Nonetheless, these worries have been resolved by CERN and the international scientific community through thorough investigation and safety evaluations. According to research, even in the unlikely event that strangelets were created at the LHC and existed, they would probably be extremely unstable and decay too quickly to alter Earth's substance in any way. Moreover, cosmic rays, high-energy particles from space, continually hit Earth at energies substantially higher than those generated by the LHC, but they don't produce any strangelets. According to this standard evaluation, strangelets don't pose a serious threat. There is a worry that the LHC may produce tiny black holes because of physics's conjectures on extra dimensions. Some theoretical models suggest that Hawking radiation, named for scientist Stephen Hawking, might cause high-energy collisions inside the LHC to create miniature black holes that would evaporate instantaneously. Experts concur that there would be no danger if tiny black holes were created at the LHC. Such black holes would initially be tiny and transient, vanishing before they could interact with the surrounding material. Second, even while LHC collisions are massive by human standards, they nonetheless involve energies significantly smaller than those of massive cosmic ray collisions that naturally occur. It is extremely improbable that any harmful outcomes from the LHC would be obtained, since no deadly micro-black holes have been seen from astronomical ray interactions. In order to make sure that experiments at the LHC do not endanger people or the environment, CERN carefully analyzes security measures in conjunction with outside boards. To address any possible concerns, these studies contain safety protocols, test data, and theoretical analyses. Even while the LHC's experiments are still pushing the limits of what we know about physics, they are done so with a great deal of care and scientific control to make sure that breakthrough discoveries are made without putting humanity at excessive risk. Rather than being realistic scientific results, speculative dangers frequently resemble science fiction. Extensive studies and natural cosmic phenomena have led scientists to conclude that experiments at the LHC are safe and that hazards are negligible. The search for magnetic monopoles, hypothetical particles with only one magnetic pole, either a north pole or a south pole, is one of the most fascinating studies that has been proposed at CERN. Conventional magnets, on the other hand, have two poles. The presence of Paul Dirac, a scientist, predicted magnetic monopoles in 1931 and showed how their existence would account for the quantization, or discretization, of electric charge. Magnetic monopoles are theoretically significant, but they have never been seen in action. Scientists are looking for signs of these elusive particles at the LHC. In addition to revolutionizing our understanding of magnetic fields, the detection of magnetic monopoles could result in significant technological advancements, such as novel techniques for the transmission and storage of energy. Moreover, the finding of magnetic monopoles would support string theories and grand unified theories, which seek to explain all of nature's fundamental forces inside a single framework through scientific evidence. Even though the hunt for magnetic monopoles may appear impossible, it exemplifies the spirit of inquiry and curiosity that motivates CERN's scientific research. A noteworthy experiment conducted at the LHC looks into the possibility of particles existing that are faster than light. The speed of light is the universe's highest speed limit, according to Einstein's theory of relativity. But according to some theoretical theories, there might be particles known as tachyons that travel faster than light at all times. Finding tachyons would pose a serious threat to our comprehension of causality and spacetime. Although the existence of tachyons is still disputed by most physicists, the LHC's hunt for them shows how willing the facility is to investigate even the most exotic areas of theoretical physics. Scientists can also perform experiments at the LHC that mimic the circumstances of the early cosmos right after the Big Bang. Moments after the Big Bang, a state of matter known as quark-gluon plasma was created by these high-energy collisions. Scientists aim to learn more about how the universe changed from its original high-energy state to the ordered and sophisticated universe we see today by examining this plasma. In conclusion, the wide range of experiments carried out at CERN, from producing quark-gluon plasma to looking for magnetic monopoles, highlight the scope and aspiration of the research done at the LHC. They show how CERN is investigating previously considered entirely theoretical fields of physics and expanding our knowledge of the cosmos. By smashing particles at extremely high energies, the LHC seeks to improve human knowledge and reveal the mysteries of the universe. This makes it possible for scientists to investigate the underlying properties of matter and the forces that control the cosmos. This intense search for knowledge is a reflection of humanity's innate curiosity and exploration instinct. The ramifications of the discoveries produced at the LHC for our comprehension of the universe are far-reaching. These studies improve our understanding of the universe's origins, evolution, and ultimate fate by probing the smallest building elements of matter and the fundamental forces at work. They assist in addressing some of the most important concerns concerning life and provide insights into the very fabric of reality. Beyond particle physics, the scientific and technical advances resulting from LHC research have real-world implications. Advanced processing systems, detectors, and data analysis methods have advanced a number of sectors, including material science, information technology, and medicine. Additionally, the LHC promotes international cooperation by motivating a new generation of scientists and researchers to cooperate and exchange knowledge and skills. This global partnership demonstrates the ability of science to bridge divides and bring people together in the search for knowledge. To sum up, the Large Hadron Collider is an essential component of contemporary physics that has allowed for significant discoveries and expanded our understanding of the cosmos. Through its experiments, fundamental particles, forces, and the origins of matter are revealed, providing crucial insights into the mysteries of existence. The LHC is a living example of the spirit of scientific research and the boundless possibilities of human curiosity, thanks to its technological advancements and international partnerships. We are getting closer to finding the answers to some of the most important issues concerning our universe and our role in it as we continue to investigate it with the LHC.